So this is the second lecture of the electric field due to line of charge. In the first lecture, we have seen the generalized formula for finding the electric field due to a thin line of charge at any point P in terms of the two angles, the angular coordinates, the initial angle and the final angle. Before proceeding with this lecture, I recommend you to watch lecture 1 if you haven't gone through it, because in this lecture, we will apply the concept of lecture 1. Now, in lecture 1, we have seen if there is a line of charge, okay, if there is a line of charge and there is a point P, so we can mark the initial and the final point of the line like this. Say this is your initial point and this is the final point and this is your perpendicular distance r, and we can take two coordinate axes, one along perpendicular to the rod away and one along parallel to the rod towards the final point. And we have seen if lambda is the linear charge density of the rod, so Ex came to be C lambda by r sine theta 2 minus sine theta 1, and Ey came to be C lambda by r cos theta 2 minus cos theta 1, correct? Where theta 1 is the angular position of the initial point and theta 2 is the angular position of the final point. And this is taken as the reference line we have seen in lecture 1. And below the reference line, the angle is taken as negative, and above the reference line, the angle will be taken as positive, okay? So this, and see, I'm not putting lambda in modulus. So this equation will give you both the magnitude as well as the direction of the components. It can be positive or it can be negative. If it is positive, Ex will point right side. If Ex is negative, it will point left side, and so is the case for Ey. So this is the end formula which we have seen how to apply in lecture 1. Now in today's lecture, we will see the special cases, how we will take some of the special cases. So 3 special cases will be of prime importance, for which the end formula must be on our fingertips. The first case is field on the perpendicular bisector, field on perpendicular bisector of finite line. Of course, we are talking about thin line, okay? Field on the perpendicular bisector of finite line. So suppose we have some line of charge of finite length, and there is a point P on the perpendicular bisector. Okay, this is a point P on the perpendicular bisector at a perpendicular distance r. And since it is the bisector, both the length above the perpendicular line and below the perpendicular line will be equal. So these two angles will also be equal. So this is the initial point and this is the final point, and say lambda is the linear charge density. Now I'm making two axes according to the model of derivation. X-axis is perpendicular to the rod away and y-axis is parallel to the rod in the final direction. Now see, in this case, sorry, both these angles will be equal, correct? If this is alpha, this will also be alpha, because point P is on the perpendicular bisector. So theta 2 will be alpha and theta 1 will be minus alpha, correct? So if you talk about Ex, so Ex will be C lambda by r sine of theta 2, that is sine of alpha, minus sine of minus alpha, and we know sine of minus alpha will be minus sine alpha. So it will be 2c lambda by r sine alpha. This came to be the value of Ex, correct? This came to be the value of Ex. Now what will be Ey? So when we talk about Ey will be C lambda by r cos of theta 2, that is cos of alpha, minus cos of minus alpha, and cos minus alpha will again be cos alpha. So Ey will come to be 0. And E will be under root Ex square plus Ey square. So E will simply be Ex. So the magnitude of electric field will be 2c lambda by r sine alpha. And it will be along the x-axis. It will be along the x-axis, that is perpendicular to the rod, something like this. So this is your electric field due to a finite line of charge at any point on the perpendicular bisector. 2c lambda by r sine alpha. Okay, this is our electric field at any point on the perpendicular bisector of a uniformly charged line or rod, thin line or thin rod. Okay. Now, as I told you, this special case is of prime importance. In many of the numerical MCQs, you will find the application of this formula directly. So we'll keep it on fingertip. Correct? We would like to keep this formula on fingertip. So remember, if we have a line and there is a point lying on the perpendicular bisector, that density is lambda and this distance is r. I'm assuming that lambda is positive, so field will be away. If lambda is negative, field will be inwards, and field will be like this. Field will be like this. See, the field will be in the same plane as the plane of the line and the target point. The field lies in the same plane. The field is in the plane of target point. Target point means where we are finding the field and the line of charge. In this case, that plane is the plane of this digital board. And you can write E as how much? C lambda by r twice of sine alpha, where alpha will be what? You can take any angle, either from the upward point or the downward point, both the angle will be same, this. Okay, so this will be your magnitude of the electric field. And if you are not putting lambdas in modulus, it will give you both the magnitude as well as the direction. See, in the model, you are making E outward. In the model, you are making E outward. So if lambda is positive, E will come to be positive. If E is positive, it means where we have indicated the E, the actual E will be in the same indicated direction. That is, E will be outward. If lambda is negative, E will come to be negative. What it means? The actual direction of E will be opposite to the indicated one. So it will be like this. So this equation without the modulus, you can use making E outward. When you are using this equation, make sure that you are making the vector E outward. Either it will come to be positive or either it will come to be negative. If it comes to be positive, the field will be outward. It comes to be negative, the field will be inward. Okay. However, if you know the sign of lambda, suppose in some problem, you are given that this is negatively charged rod. And this is a point P, and this is lambda. Of course, if it is negatively charged, the sign of lambda will be negative. And this is your angle alpha, and this is r. So of course, lambda will be negative. I'm not writing minus lambda. I'm saying lambda is negative. So the field will be negatively charged. Rod will make field inwards like this. And if you're writing the magnitude, simply the magnitude, so you can write 2c modulus of lambda by r sine alpha. Clear? Clear? So if you're writing the magnitude, you are knowing the direction, you can put modulus of lambda. If you want the equation to tell you the direction as well, you can take the model of positive lambda, make E outward, and put lambda without modulus. So E can come to be positive or E can come to be negative. Okay. Now, in terms of length, in many of the problems, we have to get the answer in terms of the length of the rod. So if you get in terms of the length of the rod, so suppose this is the rod, this is the point P, this is perpendicular distance R, and both this length are equal, and this length is L. So of course this will be what? L by 2, and this will also be L by 2, and say linear charge density is lambda. So if you make these angles will be equal. Both angle will be alpha, alpha. And assuming the positive charge model, I'm making E outward perpendicular to the rod. And since I'm making a generalized case, which will be applicable for both positive charge as well as negative charge, so I will not put modulus over lambda. So E will be 2c lambda by R sine alpha, correct? 2c lambda by R sine alpha. Now I cannot leave answer in terms of alpha, because at the very first place alpha was not given. We have to give answer in terms of length. So you can get, this is L by 2, this is R. So this hypotenuse will come to be L by 2 square plus R square under root. So your sine alpha will be perpendicular by hypotenuse. So you'll get L by 2 divided by L by 2 square plus R square under root. So you'll get L by 2, you'll get L square plus 4R square by 4, and root of 4 will be 2. This 2 will get cancelled away. So sine alpha will be L by L square plus 4R square. So your electric field will come to be 2c lambda by R, L divided by L square plus 4 times of R square whole under root. Okay, this will be the formula for the electric field. On the perpendicular bisector, electric field on the perpendicular bisector of a thin, uniformly charged rod, thread, wire, anything, to C lambda by R, L divided by root L square plus 4R square. And it is applicable for both positively charged as well as negatively charged, because lambda is not in modulus. We have indicated E outward. So if lambda is positive, it will be outward. If lambda is negative, it will be inwards, correct? Now see, let's see one of the illustration in which we can apply this equation. Say we have an equilateral triangle made by an equilateral triangle is formed by 3 insulating thin rods. Find the electric field at the center. Okay, this is the problem. We have to find, there is an equilateral triangle and it is formed by 3 thin insulating rods. Say first one is positively charged. This is a rod with a density lambda. So second one is also positively charged, again with a density lambda. And third one is negatively charged, say with a density minus of lambda. And this is the center, and the side of the triangle is L. And we have to find what will be the electric field at the center of the triangle, okay? Now if you see, the center will lie on the perpendicular bisector of all the 3 rods, correct? The center will lie on the perpendicular bisector of all the 3 rods, number 1. Okay, this is first property which we can see by basic geometry. G will be on perpendicular bisector of all three rods. Okay, and by symmetry you can see all these three distances will be equal. Let it be R. Let it be R. Okay, now we have to find R. What will be R in terms of L? Because we have to give answer in terms of L. So one of our goal will be to find R in terms of L, for which we are going to use the basic geometry. So we can make a equilateral triangle. If this is an equilateral triangle, and this is the perpendicular bisector, which will also be the median in case of equilateral triangle, and this is the centroid, and this is length L, and say this is A and this is B. So this distance is R, correct? The distance of the center from the side. So this angle will be 60 degree. So AB will be the projection of L. So AB, now if you see this length, this will be L cos 60 degree, and this will be L sin 60 degree, correct? This is L sine of 60 degree. So L sine 60 degree, that is L root 3 by 2. L root 3 by 2. Now we have to find GB. Now we know the basic property, the centroid divides the median in the ratio of 2:1 from the vertex. So GB will get one part out of 3. One part out of 3 of the length of the median AB. So it will be 1 by 3 L root 3 by 2, correct? So what will be the answer? You will get this length as L 2 root 3. This is the value of R. L 2 root 3, correct? This is the value of R. Now what will be the electric field? Let us name the three segments as segment 1, segment 2, and segment 3. So from the fundamental knowledge of this thing, the field on the perpendicular bisector of finite line, the first vector, electric field vector 1 for segment 1 will be like this. The second vector will be like this. Both are positively charged. So field will be away. This will be E1 and this will be your E2. Now what will be the magnitude of E1? You will say C. And since I'm making the direction, so I can put lambda and modulus, correct? I can put lambda and modulus. I'm simply writing the magnitude because the direction is known, it is positively charged. So I'll get C 2C lambda by R length by L square plus 4 times of R square, correct? Now what will be E2? E2 will also have the same magnitude because lambda is same, R is same. So 2C lambda by R L divided by L square plus 4R square, correct? Let it be equation number 1 and equation number 2. And let the field because of the third segment be E3. So E3 will be inward because it is negatively charged along this line, perpendicular line. This is your E3. And what will be E3? 2C modulus of minus lambda, that will be same as modulus of lambda by R, length is L, L square plus 4R square. So you can see all the three vectors have the same magnitude, though they don't have the same direction, but they have the same magnitude. Now we have to add the three vectors. Okay, so let vector E be vector E1 plus vector E2 plus vector E3. Okay. Now for adding the three vectors, you can use the component method. You can take y-axis, x-axis, take the components or add. This is one method. But there is one more better method, parallelogram law. But the limitation of parallelogram law is that at a time we can add two vectors. So fortunately, if you see E2 and E1 have the same magnitude. So say vector E0 is the sum of E1 and E2, correct? And I'm making a clear figure for E1 and E2. This is your E2 and this is E1. And what is the vector angle between them? So this angle will be, by basic geometry we know, 120 degree. 120 degree. So both vectors have the same magnitude. So their resultant will be the angular bisector like this, which we have given the name E0, and this angle will be 60 degree. And we know the basic in vectors, if two vectors are of same magnitude and the angle is 120 degree, the resultant is also of same magnitude. If one is of magnitude A, another is of magnitude A, and the angle is 120 degree, then the resultant will also be of magnitude A. If you remember this thing, you can directly write E0 will be either E1 or E2. Or suppose if you don't remember, it is not striking you, you can apply the formula for the resultant of two vectors of equal magnitude. E0 will be 2 multiplied by common magnitude, that is E1 or E2, cos of the angle between them by 2. So I'll get 2 E1 cos of 60 degree, cos 60 degrees 1, sorry, half. So you will get 2 cancelled away. So answer will be E1 or E2, whatever you may like. So E0 came to be what? E1. Let it be equation number 4. Now we got the resultant of E1 and E2. And now what is left? E3. So now vector E will be E0 plus E3. Now what is the direction of E3? So E3 is also coming along the angular bisector of these two vectors, or along the median of this bottom side. So vector E3 is along this line. Now again we got some luck, right? E3 and E0 are along the same line, so it became 1D case. So we can remove the vector sign and we can write vector E is E0 plus E3, and E0 came to be E1 plus E3, and E3 also has the same magnitude as E1 or E2. So therefore, E came to be twice of E1. Now put the value of E1, that is 2c lambda by r. So E will come to be 2 into 2, 4 c modulus of lambda by r, L divided by L square plus 4 r square whole under root. This will be your final answer. This will be your final answer. And what is r? Finally, you can put the value of r, which we have found geometrically, L by 2 root 3. Okay. And if you see the final figure, if you are making the final figure, what will be the direction of the field? So that was positively charged. This is positively charged, and this is negatively charged, and this is the centroid. So we have seen the field is vertically downward, something like this. So this is your electric field at the centroid with this much of magnitude. Okay. So this is one of the illustration. We have seen the application of the field due to a finite length on its perpendicular bisector. So this is the formula which will keep on fingertip for the electric field due to a thin rod on its perpendicular bisector. That is first special case. Got it? Now we will see the second special case. We will see the electric field due to an infinite or very long line of charge. This is also very important. Electric field due to infinite or very long line of charge. Okay. So this is also very important. So suppose we have an infinite line. Infinite means both the points, the top point and the bottom points are very far, and say this is a distance r. Okay. See, either you can say infinite rod or wire or line, whatever you like. Or you can say, suppose we have a finite length. So this is L. And the point is lying somewhere near the center. Point is lying near center, and it is given R is much less than L. R is much less than L. So it will be the same model. It will be the same model, because if you come very close to the line, so your top point and below point will have angular coordinates approaching 90 degrees. So either you can be given the language infinite rod or wire or line, or you can given the language like this: we have point near the center, and R is much less than the length of the rod. Okay. So see, in this case, if you see the initial point, if there is something going up, and say the point is not seen or is very far, so if you see directly like this, the angle will be 0 degree. Now, as you are moving your eyes up, the angle is increasing. As you're going further, the angle is further increasing. And ultimately, it will approach 90 degree for the above point. So in this case, theta 2 will be 90 degree. And theta 1 will be minus 90 degree. And same is the case for this model, if this is given. Okay, if this is given. So you will get, I'm taking the two axes, x and y. So Ex will be C lambda by R sine of 90 minus sine of minus 90. And sine minus 90 is again sine 90. So C lambda by R twice of sine 90. So we'll get 2C lambda by R. This is your Ex. And what will be Ey? C lambda by R cos of 90 minus cos of minus 90, and cos 90 will be 0. So this will be 0. There will be no y component of the field. So the net field will be perpendicular to the rod. Net field will be perpendicular to the rod. How much? 2C lambda by R. Again, I'm not putting lambda in modulus, giving consideration to both positive lambda as well as negative lambda. So this is second fingertip formula, which we will keep in mind. Okay, the electric field due to infinite or very long line of charge. So whenever we will keep it on fingertip, whenever we have infinite line or we have finite line, point is somewhere near the center, and R is much less than the length of the rod. It is the same model. Tick. So your field will be away, considering positive lambda model. Considering positive lambda model, E will be perpendicular to the rod, away, and will have a magnitude 2C lambda by R. Got it? So this is the second fingertip formula for infinite line of charge. 2C lambda by R, field is perpendicular to the rod, positive outward, negative inwards. Now we'll see the third model, which is also very important, especially for competitive problems. Electric field due to semi-infinite rod. Now, what is the meaning of semi-infinite rod? one end is at finite position and another end is very far away, like this, something like this. Okay, so this point is going to infinity, and suppose this is the target point. This is the target point at a distance r. And same model will be, suppose we have a finite line and there is a point P at the end. Now we have a finite line and the length of the rod is L and you are given R is much less than L. So it is the same model, okay? Either you can be told that the line is semi-infinite or you can say the point is located at the end and R is much less than L. See, in this case, I'm taking the two axes. This is your x-axis and this is your y-axis. And if you see initial angle, this is the initial point. The final point is at infinity. So theta 1 is 0 and theta 2 is what? 90 degree. For both models, it is the same. So Ex will be C lambda by R, sine of 90 minus sine of 0. So we'll get C lambda by R, correct? And taking positive lambda model, Ex coming to be positive, so it will be like this. Now Ey will come to be C lambda by R cos of 90 minus cos of 0. So I'll get minus C lambda by R, and taking positive lambda model, Ey is coming to be negative, so it will be downward, correct? Now you can see modulus of Ex is same as modulus of Ey. So when you will find the electric field, it will be the perpendicular bisector, angular bisector. When you find the electric field, it will be the angular bisector because both the components are equal in magnitude. So this whole angle is 90, so this will be 45 degree. And E will have a magnitude Ex square plus Ey square whole under root. So I'll get C lambda by R root 2. This is your electric field at the end of a semi-infinite rod or a finite rod where the distance is much less than the length of the rod. C lambda by R root 2, okay? Now what we have to keep on fingertip? Now suppose you are given some semi-infinite rod and there is a point P from the end at a distance r and it is density lambda and say it is positively charged. And if nothing is known about sign of lambda, take the positive charge model. So see how you will make the electric field. First of all, extend this perpendicular line. The field will be downward with this line at 45 degree away. Downward at 45 degree away. Got it? And if it is negatively, negatively charged rod, say minus lambda, and lambda is something positive. So your field will be again at 45 degree with the perpendicular inwards above the line. Inwards up. This is away, downwards, correct? And if you know the sign and you are simply writing the magnitude, you can write E is equal to 2c c lambda root 2, put lambda in modulus by r. Here you can write E is equal to minus lambda modulus will be same as lambda, E modulus lambda root 2 by r. If sign is known. If sign is not known, okay, if sign is not known, suppose I have given you a line, lambda with a density lambda, uniform line with a density lambda, and there is a point P, and you have to make the field at P. You don't know whether lambda is positive or negative. Make according to the positive model of lambda. Take positive lambda model and don't put modulus. Don't put mod. So you will make E outward and below the perpendicular line 45-degree E, and this is R. So you will write E is C lambda by R root 2. Now see, I'm not putting lambda in the modulus. So if lambda is positive, E will come to be positive. If lambda is positive, E will come to be positive, which suggests what? The actual direction of E will be same as the indicated one. If lambda is negative, E will be negative, which suggests what? The actual direction of E will be opposite to the indicated one. Okay? So this is how we have seen the three fingertips formula. One is due to finite rod along the perpendicular bisector, one is due to infinite rod, one is due to semi-infinite rod at the end. And same model will be applicable for this thing at the end if R is much